take a break in a minute. Okay, so atomic mass. The other thing on the periodic table is under the element symbols are more numbers. And those numbers are not nice round whole numbers, are they? They've got decimal places. Like under carbon it says 12.01. So we're going to talk about what that is. That's the atomic mass. There are multiple isotopes for many of the atoms. And yet we only see one atomic mass listed on the periodic table. We're concerned about the average mass of an atom. And so we take the average mass of all the isotopes of an element, and that's what goes on the periodic table. And how do you do that? Well, it's a weighted average because they don't all have the same distribution. So if we look specifically at chlorine, 75.77% of all chlorine atoms are chlorine 35, and 24.23% of them are chlorine 37. And so we take the average of those two, and yet it's not 50-50. So this is the general formula for that. We take the atomic mass will equal, you take the percentage and turn it into a fraction, you multiply it, you turn it into a decimal. You multiply it by the mass of that particular isotope, and then you add that to the percent turned into a decimal times the mass of the other one. And here they're listed in atomic mass units. If we look at this, chlorine 35, its mass is very close to 35, isn't it? 35 means it's got a total of 35 protons and neutrons altogether. So we would expect its mass to be 35 atomic mass units. Well, it isn't exactly, but it's really close. Chlorine 37 has a mass that's very close to 37. So in a problem like this, they'll give you the percent abundance, and they'll give you the mass of each of the isotopes, and they'll ask you to calculate the average mass of an element. So here's another way, more general. You take the fraction of isotope 1 times its mass, and the fraction of isotope 2 times its mass, and blah, blah, blah. There could be more than 3. Then you add them all up together. This is one of those topics that if you don't grasp this, you can still pass the class. We teach it to you, it's important, and yet it's not critical to your success in the rest of the class. So if you're trying to figure out what you can skip, you could probably skip this one. So let's do this guy. So we're given 3 different isotopes here, isotopes of magnesium. They give us the masses of each of them and the natural abundances. So we need to take the natural abundance and convert it from a percentage to a fraction, a decimal. So you do that by dividing by 100, or just moving the decimal point over. So the first one is 78.99%, so that's 0.7899, times the mass of that one. Well, that one was 23.99 AMUs. Plus the next one. The next one is 10%, so that's 0.1000 times 24.99 atomic mass units. Plus the third one, 11%, 0.1110 times 25.98 atomic mass units equals. And you can just do all of this on your calculator. So you can just type all these in, and your calculator can handle it all at once. So 0.7899 times 23.99 plus 0.100, if you want to put those zeros in, times 24.99 plus 0.1110 times 25.98 equals, and my calculator is telling me 24.332481 atomic mass units. Of course, that's a ridiculous number of significant figures. We could do the mix, because we've got adding and multiplying mixed up here together, but what it's going to come out to is whatever number of decimal places you had on your atomic masses. So here we've got 2 decimal places, so we're going to end up with 2 decimal places here. All of our percentages have 4 significant figures, and so we're good to round this off to 4 sig figs, 24.33 atomic mass units. Now, when you're doing an actual element that exists, you can check your work by looking at the periodic table. And the number we have on this periodic table is 24.31, and we came up with 24.33. It's only differing in the uncertain digit, and so we can be pretty sure that we did it correctly. If you come up with an atomic mass that's larger or smaller than the largest or smallest atomic mass, something went haywire. Okay? It's just like when you average 2 numbers, the average has to be between the numbers. Right? It's kind of the nature of averages. Isotopes do have significance. Some isotopes are unstable, where other isotopes of that same element may be stable. The unstable ones will tend to fall apart. You can think of it that way. They will emit radiation, nuclear radiation. They'll spit out some of their subatomic particles. And so if an isotope does that, if it's shooting out electrons or something, then we say that it's radioactive. So some isotopes are radioactive. I think we all have maybe more than a healthy fear of nuclear radiation. Is nuclear radiation good? Is it good for you? No, stay away from nuclear radiation, right? Well, no, it's not good for you. And it can really damage your body because it interacts with the chemicals in your body and causes them to change. Some things are more dangerous than others, and some are more long-lasting than others. Some radioactive isotopes give off all their radiation very quickly, and then they're done, and then they're stable, and then they're not dangerous at all. And others, like Pu-239, can remain radioactive for, I don't think we really know how long, thousands, millions, billions of years. It's just going to sit there and give off radioactive radiation. There are beneficial uses of radiation. Technetium-99 can be used in conjunction with imaging in a hospital to help diagnose problems in your body. And so there's a lot of radiation that's used in medicine. So it helps them to image your internal organs. It's hard to, you can't just take snapshots of your internal organs. And x-rays are useful, and things like CAT scans and MRIs are useful, but they don't always tell us everything we want to know. And so sometimes they'll either inject you or have you swallow a radioactive substance that's not going to harm you, unless you, if you did that every day, it would harm you, but, it's a small amount, and that allows them to take a different kind of picture of your internal organs, and could save your life. They don't mention it there, but radioactivity is also used to treat cancer. They can use radiation to kill cancer cells. And so there are so many good uses for radiation. It's not something that just is horrible, and it is natural. Okay, people think that, if this thing is natural, it must be safe. Well, tigers are natural too. Tigers aren't safe, right? So just because something's natural does not necessarily mean it's safe, right? But radiation is natural. It is, and yet it is not necessarily safe. But it's not necessarily evil either. So there's two sides to everything. So here's the end of chapter 4. Just kind of a summary of the different things that are covered in that chapter. Chemical skills. So the previous ones were things you should know, and these are things you should know how to do. So determining ion charge from the numbers of protons and electrons. Determining number of protons and neutrons from isotope symbols. We did those things in class. And that's the end of the chapter.